Hey everybody, we are going to talk about radiation. That's why I'm wearing my helmet. It's going to protect my brain, which is huge, from all the radiation. What we're going to talk about is how alpha, beta, gamma, and how they ionize stuff. Then we're going to talk about how that can affect your body. And then we'll talk about why those nuclei are unstable in the first place and may want to go through that decay stuff. The good question is, how much do these different decay particles make things ionize? Now, to ionize is when you take a molecule. Let's say that these are air molecules or nitrogen. If you ionize one, you take an electron and you excite it so much that it's like, whoa, and it takes off. It goes off to live a crazy life of its own. That is to ionize. So when this alpha particle, which I drew as a fish, comes through here, it is a strong ionizer. And it makes all these electrons, they're like, wow, 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 wow. They are all having ionized electron parties somewhere far away. Beta particle, it is a weaker ionizer. When it trucks through here, a few of these electrons are going to come off, but not near as many as the alpha particle. And the gamma particle, even though it's very good at penetrating through concrete and lead, it's a very weak ionizer. And maybe only one is going to come off. Ionizing ability is not the same as penetrating ability. Speaking of their penetrating ability, if you have an alpha particle, it's just going to be stopped by a bunch of air. What a wuss. The beta particle, you might need to put a book here because it is stopped by maybe a bunch of paper or maybe a thin piece of metal. However, this crazy gamma particle can get through a lot of stuff. It can get through lead, maybe some thin concrete. It's going to take a lot of stuff to stop these crazy beta particles. Now you're going to find this crazy, but ionizing your molecules is bad. It's going to cause things like maybe some of those molecules and cells might have mutations. Maybe they could become cancerous. Bottom line is, you don't want to be exposed to too much radiation. Now you've got all this decay happening because nuclei are unstable. And let's ask the question, what makes these nuclei unstable? To help you understand that, we have this graph here of the number of protons for an element versus their number of neutrons. Now for a while you've got things like carbon that usually has like 6 protons and 6 neutrons, and nitrogen, 6 protons and 6 neutrons, and at first all the elements have about the same number of protons and neutrons. And if you make a line that goes through all of those that have 10 and 10, 20 and 20, 100 and 100, you're going to end up with a line that looks like that. And you'll see that as the elements get bigger, they start having more and more neutrons. And the reason for that is that you've got this strong nuclear force. It's kind of a funny force, whereas it needs a very strange ratio of neutrons in there to keep a nucleus together. If you have up here, if you're this thing here, we're going to call our stability line. This is where most of the ratio of neutrons or protons actually exists. Up here, where you'd have excess neutrons, that's not good. Too many. And you're going to go through a type of decay that gets rid of neutrons. And if you think back, what's going to eliminate neutrons? That is going to be beta decay. Because you can think of it like a neutron is splitting into a new proton that stays there and an electron that flies off as a beta particle. If you are down here, you have too few neutrons. Again, the nucleus is not stable, so it's going to decay by positron emission. Now, for some reason, the IB doesn't have you go into this much, but a positron is the antimatter particle of a beta particle. And if you are up here, where you have big elements, you are going to have alpha decay.